Okay, the statement was proper sized geometrical deviations on the rail surface causes squats. To be honest, I misheard a question mark at the end. It was with a question mark originally. The idea behind the statement was that geometrical deviations, initial geometrical deviations, are just an example for some local anomalies which can lead to local variations of the contact conditions. And these local contact conditions can continue and lead to some local behavior on the rail surface which may lead to squats.
Okay, thank you very much. And then
regarding micro CT, so the largest sample that we actually tried to get through was around about 10.5 centimeters, which is a lot of steel because obviously steel is very, very dense, which is why typically you don't try to X-ray it. So it actually performed an awful lot better than we initially expected. And it did pick out a majority of the structures. The resolution at that level is good enough to be able to tell how big your defect is. Unfortunately, obviously hauling a CT scanner down the railway track isn't really a practical option. But if a couple of volumes of different defects from different environments were catalogued and grouped together, they could be compared to each other quite easily, because once you have this volume, you can move through it and you can compare two totally different defects really easily. So I think that's how CT data can be used best, is more of a comparison method.
okay, so please.
At the end of the day, we see white etching layer as the biggest issue out there. Keeping control of your white etching layer enables you to maintain a rail surface that you can maintain and manage going forward and prevent other defects occurring, and regular grinding and removing of that white etching layer will enable you to maintain that situation effectively.
Thank you very much.
So for us it's very important, it was very important to show that with rail milling you can contribute to squat mitigation, being capable of removing even deep defects, adjust the profile accordingly, and do this in a way that you remove all initiation points but also do not introduce any new initiation points. However, very important to highlight, it is a contribution to mitigation but not a solution to the problem.
Okay, thank you very much. So, any question? Yes, please. Sorry.
I have a question for Richard Stock. Whenever you grind a rail to remove a squat, you also grind some nearby parts of the rails that are not damaged. And therefore you remove the top of the rail, which is normally head hardened. So you remove a part of the rail which lasts for a long time because it increases its mechanical properties. When you mill up everything and you bring to the surface fresh material, which was not previously deformed or head hardened, do you expect to see any more wear in the rail, or the head hardening is immediately coming after the rail milling?
So there are two aspects. First of all, if we talk of heat-treated rail, usually this heat-treated zone, standard rail. Well, you talk about the plastic deformed layer, the work hardening. Well, usually to our experience, depending on the traffic levels, the rail adopts very quickly to the traffic that goes over the rail and reacts with plastic deformation and work hardening. So even if we cut down 2 millimeters because we have the deep cracks, yeah, after a few trains, the rail condition on the surface will go back to meet the loading of the trains, to say so. So I don't see this really as a problem. I think that this will come back very quickly.
I've got a question to everybody here. That there seems to be a bit of a difference of opinion about the significance of white etching layer. And Sean in particular, I think, has suggested that it's actually just thermal damage, but you don't actually need the white etching layer. So would you like to comment on that?
Yeah, Yeah, when I talk about thermal damage, I'm not really referring to the white etching layer too much. I've looked into the white etching layer and it is present in islands, but because white etching layer exists across all of the rail, I wasn't looking at that to be the cause. I was looking for something that was only existing within the defect. So yeah, by thermal damage, I'm referring to grain refinement rather than the white etching layer.
Okay. If I can give a comment here. As Richard said, white etching layer appears on most railway systems, and you can find white etching layers on most rails, but not on all rails. You find squats or studs or new squats. And as you saw in our test rig results, white etching layers can lead to cracks, outbreaks, cracking the base material, and so on. But that doesn't mean that such cracks or outbreaks can develop into a squat or in a stud or in a new squat. It can just be the initiation point for the development of a squat. I think it's a very complex problem, as we also have seen in Richard Stock's presentation, and that it's not just white etching layer which causes squats or studs.
I think in the majority of our situation, we have found white etching layer and squats at the starting point. Invariably, when we pull the squat to bits, the white etching layer has disappeared, which we think has happened in the initial crack and then fracture of the surface material. But in looking at the mechanics of the situation, I think white etching layer forms an enormous role in the situation.
So I think there's not much to say except that yes, white etching layer can be one initiation point of many, to say so. It's really important to understand, I think, what is the characteristic of such a white etching layer that causes a problem versus the characteristic of a white etching layer that does not cause a problem. So it's a complex system.
Also, with the with one of the samples, the one that I've done the higher resolution scan on, I believe the initiation on that one was subsurface. So obviously, and then cracks are working their way up to the surface as you get more mobility as the crack detaches the upper material. So when you're getting subsurface initiation, obviously, you're worrying about white etching layer less, although it obviously is affecting the tribology of the surface.
So, wait a minute. So in Japan also the white etching layer is a very big problem, and but a very interesting story that Shinkansen, the high-speed rail, is very nicely managed to the wheel profile, maybe some, and also the traction. So the smooth acceleration and the braking also smooth. So Shinkansen is a very long length of the track, but almost no white etching layer. But of course, conventional line, many white etching layers. So one of the solutions is that good control of the traction or something like that. But it's just a very limited condition. So, yes, please.
Yes. I would like to ask the panel for a joint opinion on whether they consider squats as rolling contact fatigue or not, because I've seen very divergent opinions on that. So do you believe that squats make part of the rolling contact fatigue family, or is it a completely independent thing? And I have not seen something convergent on that.
That's a very good question. If you look at that, what we saw in the 70s, yeah, a lot of plastic deformation, definitely a ratcheting-driven defect. Here, this defect appears within 10 MGDs, so ratcheting wouldn't be the cause for such a defect. Yeah, I think also Stuart published a paper on this. And so, if it's not ratcheting, perhaps it's not RCF, but I'm not entirely sure.
Are we talking about new squats or kind of the original squats that we talked about, just to clarify? The new ones, are we saying?
Yep.
Yeah. Oh, yeah. No, I wouldn't. I'd consider them a non-RCF. Yeah. Because I don't see much plastic deformation on the surface or much ratcheting. The only plastic deformation I usually see is when if a crack is so acute that it thins out the surface, you might get a little bit of plastic deformation, but generally it's quite remarkable how little deformation there is on the surface. So it doesn't appear to have ratcheting. From the few samples I've seen, I'll just clarify, these are the only 3 samples I've ever looked at that get understood, so it's a limited answer.
So I sort of regard it like skin cancers. RCF are malignant skin cancers. Squats are benign. Squats tend to hide a lot of other issues. Bad RCF leads to broken rails. RCF, so we keep them in 2 very different patches, and have been able to manage our network now for almost 10 years under those conditions, and lived with a lot of squats out there.
Are the defects that you are talking about, you call them squats, but according to the terminology that Ishard is using, would that be studs?
They're studs.
They're studs.
They're studs. Yeah.
So the question is related to what is rolling contact fatigue? So it's a big question. Anyway, yes, please.
Thank you. Do you think this terminology, squats and studs, can be dependent on the hardness of the rail?
Within the ones I looked at, they were all R260.
Yeah, because I think before hard rail was introduced, we all call this squats, yeah? After the hard rail started to be introduced in rail operations, we started to call, some of them started to call studs. So this is a question. Is it dependent on rail hardness?
So in our network, squats are the old style. Stuart came forward and introduced us to the stud term, so I appreciate that. With our work with Wollongong, we find that the RCF squats have a different stress plane to the stud in the crystalline structure. And that's how we identify, when we pull them to bits, what's going on. So we've had a situation where we've had studs right through an area of RCF, but we were able to clearly demonstrate by the crystalline structure that it was actually the squats that were breaking the rails. So at microscope level, there's 2 different ways to define them. For track walkers, it's quite difficult, and life gets quite interesting out in the field.
So this question, it's not the first time that this question comes out about heat-treated rails. Are they more prone to squats or not? To be fair, I'm coming from the rail production side, so I've worked a lot on this topic in my past. I would say the wear behavior of the system is very important. Yeah? So a heat-treated rail is supposed to have low wear. Yeah? So whatever you do with such a rail, you need to be aware of this and perhaps adjust the profile slightly different in the beginning so that you can adapt to this. I would not reduce it to saying it's this grade or that grade. You really need to look at the system and how a specific rail grade, profile combination, wheels are reacting in this system. And I think that would be a more general way of looking at the thing and to find a solution. So I would be hesitant still to point at a specific rail grade if it might be more prone to a stud development or not. We can discuss it later.
Richard, you said all new squats, or most new squats now, are studs. Can you say a bit more about why that's the case and if it's true across all networks? And also, would you include squats on joints or welds as in your definition of studs, or do you think maybe that's a third type of squat, which you don't know so much about?
So, if I understood your first question is, if I would say, why I would say that well, we have looked at a lot of defects in my past, but also recently, and we have seen, for me, the clear differentiation is, do I see a lot of plastic deformation or not? Yeah. And with all the defects so far, I hardly see plastic deformation, and all the other researchers that have looked at this kind of found the same. On welds, again, that might be a different story. It depends on the microstructure in the weld, how such a defect might develop, if it's more like a stud or more like a squat. But I did not specifically look at welds in this case, so I might not be the right person to ask the question.
I have, if you would like to have a chat later.
Yeah, I'll talk to you later, thanks.
No, okay.
Okay, thank you very much for the time. It's just coming and.
Thank you very much.